In our last video, we looked at product rule for following when we had one function multiplied by another. However, we will also see functions divided by one another, a quotient, and it's worth quickly covering these with quotient rule. In the last video, we showed the expression for product rule as duv by dx is equal to u dv by dx plus v du by dx for when two functions of x, u and v are multiplied together. Let's now look at what happens when the function u is divided by v. Again, for the purposes of linking to texts, you will often see quotient rule written as du over v by dx is equal to v du by dx minus u dv by dx all over v squared. This looks quite daunting, but again, let's look at it in context with our two previous functions, f of r equals 2r plus 4 and g of r is equal to r squared plus 10. We will try and find the first derivative for f of r divided by g of r. Firstly, we write down the derivatives of each of the functions, and as f of r is on top of the fraction, we will label this as the u function, with g of r being the v function, along with their respective derivatives. We now look at the expression for quotient rule and we can start to put our values into this equation. It starts to look messy quite quickly. By being methodical, we can obtain an expression for this derivative. Often, we are able to identify ways of cancelling our coefficients, but otherwise we are able to use our derivatives appropriately. Again, we will look at a chemical example. Let's look again at the example used in the previous video, that of the radial distribution function for a hydrogen 1s orbital. If we want to identify the peak of the distribution, we look for the point where the gradient is zero, i.e. the first derivative. We looked at this function using product rule, assuming there were two functions multiplied together. However, look again at the equation. We have a negative index on the exponential term. This means that formally this is a quotient, and we can write this alternatively as such. This time it does matter which one we ascribe as u or v. So let's say, as it's on the top, u is equal to 4 pi kr squared, with du by dr being 8 pi kr, while v is equal to e to the power of r over a. dv by dr becomes 1 over a times e raised to the power of r over a. We now use these results in our application of quotient rule. Laying this out, it looks quite messy, but our overall result is this. It does look messy compared to that which we found in the previous video, but let's look at what's in common. On the top, there's a common factor of e to the power of r over a. This will cancel with the value at the bottom of the fraction. Now if we want to find the maximum of the graph, we set this to 0, and as we work through, we still get the same results we got before, r equals 2a. Product rule and quotient rule are simply applications of the same principle. Often product rule is seen as being the easier of the two to consider as there's less complexity involved, and if it is possible to rewrite your functions as a product rather than a quotient, this can offer an alternative route to check your results. If you have more than two functions multiplied together, for example f of r, g of r, h of r, it is possible to use a repeated application of product rule to determine the overall first derivative. Firstly, apply product rule to find the first derivative of f of r, g of r, and then apply product rule a second time, using f of r, g of r as u, and the first derivative of this as du by dr when combining with h of r. These all start to look very complex, but the important aspect of this is there is often more than a single way to find derivatives of such functions. It is simply a case of identifying where you want to start and sticking with it. If there's a second way to find the derivative, you can use this as a means of checking that you have correctly applied the relevant method. In the next video, we'll be looking at what to do when we have chained functions, that is, when the output of one function feeds into a second.